non-negative curvature.
Thank you, Marcus. Yeah, I'm quite honored to be the second speaker from Stony Brook today to speak at this celebration of IMPA's 50 years. And I'm also the current chair of Stony Brook, so I want to convey our congratulations. We have had a lot of relations, mathematical relations with Brazil in the past, and in particular with IMPA. And of course, I have a number of friends here, Manfredo, Marcus, Lucio, Luis, and it's always wonderful to be back. Yeah, I've never taken the difficult step to move into algebraic geometry, so I have, in fact, in this talk, in some sense, I returned to some of my my early work in differential geometry. So I want to talk about spaces of non-negative sectional curvature and some new rigidity aspects which seem to become very important recently. Yeah, so let me. Oh, did this get? Or did this get there? Yeah, so how rigid is non-negative curvature? So we consider a connected Riemannian manifold, always assume it's complete, and let me, so it should have non-negative or positive sectional curvature. Let me remind you how that can be viewed in the most geometric way, and that's via Topanograph's global comparison theorem. So whenever you have any geodesic triangle, then you can, in the manifold, then you can find a triangle with the same side lengths, and then all corresponding angles there will be smaller. The curvature bigger means angles are bigger. Yeah, so that's of course locally always true. But that it's globally true is a relatively deep theorem of fundamental importance in global Riemannian geometry. The condition of any sectional curvature condition is, of course, always corresponds to a system of partial differential inequalities, which is never treated that way, rarely treated from the viewpoint of analysis. And for Ricci curvature, one does that, but for sectional curvature analysis is of little use. It's highly overdetermined, and therefore it should have some very strong rigidity properties. Of course, locally, positive curvature is an open condition. But globally, the rigidity aspects usually are important and come about in the global setting. Yeah, so I want to maybe first give a brief review of what is known in the topological situation, and then the main topic of my talk will concern the metric situation, metric rigidity. Yeah, so topological rigidity basically is reflected first that there are not very many examples. So let me just summarize. The only thing that has always been known since the early days of Meyer's theorem and is something about the fundamental group. And in fact, the structure of the fundamental group is basically understood. I mean, there are some questions, in fact, a number of interesting questions left, but basically, the fundamental group is not really the problem here. Yeah, so roughly the fundamental group, in the strictly positive case, it's finite, and otherwise it's not very far away from a Bieberbach group, like in the flat case. Yeah, so it's a finite normal extension. It's a normal extension of a finite group by a crystallographic group. So basically, I just want to assume the manifold is simply connected. And then, of course, the geometry is very simple. The curvature is constant. Then we're just basically dealing with the standard model geometries of spheres in Euclidean space, and which is, again, very different from Ricci curvature and scalar curvature, where the standard model spaces are not unique in any or rigid in any way. Yeah, so let me first discuss the compact case, and it cannot be pointed out enough. So in the case of strictly positive section curvature, essentially there are only many examples, some more examples in small dimensions. So the dimension is at least 24. The only examples are spheres and projective spaces, very classical geometries, topologically. And in fact, in R dimensions, it's, remember I assumed it's simply connected, there are only spheres. So in the dimensions bigger than 24, I've said it many times before, but I want to say it again, we have essentially only one example. And that is not very, very good. For smaller dimensions, there are some more, and there are the famous sequence of Eschenburg from '82 in dimension 7. Most of these examples came, except for very sporadic examples, came from the construction of bi-quotients. Yeah? So basically, what you do is you take a Lie group with a good metric, usually a bi-invariant metric, which has non-negative curvature, and then you divide from the left and from the right simultaneously. If you only do it from one side, you just have homogeneous spaces, but if you do it from both sides, you have so-called bi-quotients, and they have given rise to a good number of very important examples. So there's this infinite string of the Eschenburg examples, which has there are lots of interesting aspects to them. They, in fact, not all of them really have strictly positive curvature, only half of them. But there are many, many examples that have their sort of homeomorphic but not diffeomorphic, and all kinds of Einstein metrics, all kinds of beautiful features in this sequence. The other sequence, not so well known, is the string of Berzeikin from '96, which is also a double quotient of SU5 over letting SP2 cross S1 act from both sides. Yeah, so this is essentially it. Yeah, so now, non-negative curvature, people always say, here we are in good shape. There's an abundance of examples. But if you look carefully, then actually it is quite clear that there's also a lot of topological rigidity. There are not all that many examples. So the obvious examples you can construct are the ones you take products of two manifolds of non-negative curvature. And then the next construction is if you divide, yeah, if you take quotients. Yeah, so that is, you have a Riemannian submersion of a space of non-negative curvature onto something, then submersions, you can, again, most geometrically think of them as vibrations where the fibers are everywhere locally equidistant. Yeah, that's, they have the property so that the curvature goes up when you look at horizontal curvatures upstairs. They are the ones perpendicular to the fibers. So the projection is curvature non-decreasing. And so obviously then if you have something on non-negative curvature, you go to quotients, then you have again a non-negative curvature. So that contains basically almost everything we had known so far. Namely, what was known, well, I mean, you take a manifold and, for example, any free isometric action by a Lie group. Yeah, then obviously the fibers are equidistant, and this is contains this construction contains, for example, homogeneous spaces, and it also contains all biquotients. So that was the status until. Let me show you this independent slide here, just to get a feeling what it means to divide out by something. Yeah, so the fundamental construction that has been used for a long time is to take a killing field, to take an isometric action of the real line. Suppose it's free, well, locally it's always free, and look at quotients, and then what happens. So for example, the simplest situation is this picture here. When you take, it's always surprising to unless you have done it yourself, then it's surprising. You look at flat Euclidean space and take a glide rotation through helices. Yeah, and if you take the quotient, you get a convex surface, which is rotationally symmetric, which is not a paraboloid, so which is asymptotic to a cylinder. Yeah, so this is sort of the fundamental basic picture of what happens under Riemannian quotients in this situation, how the metric gets folded up. Yeah, so you, it's always wherever you, I mean, as soon as you have an action, you have an R action. Yeah, and then what happens to the metric in some sense is this bending up in an asymptotic way. So, yeah, so the quotient constructions are basically provide a lot of examples, and what one usually cannot do with sectional curvatures in any nice way is do connected sums or do bundle constructions. However, very recently, some bundle constructions come up in a new way of finding examples, and that was the by now celebrated work of Gromoll and Ziller, who considered cohomogeneity 1 actions, so Lie groups acting where the generic orbit, the principal orbit, has codimension 1. And there are lots of examples of those. In fact, Blaine was one of the first to look at them from a more topological point of view. Yeah, so the cohomogeneity 1 manifolds turn out to be quite abundant. And in fact, what Gromoll-Ziller discovered is that they're more abundant even than we think. Now, they were able to construct lots of interesting new examples. So for just one surprising string was were the famous S3 bundles over S4, yeah, which contained many of the exotic 7 spheres. Not all of them. Not all of them are fiber, but depending how you count, 10 or 14 or 15 out of 20. It depends on the orientation. So, so they're classified by 2 integers, the pi3 of SO4, and then you can think of them as being twisted together by unit quaternions in the way Milner already described it in his famous paper. Yeah. So, and the amazing thing is that they turn out to be cohomogeneity 1 manifolds, which is not obvious at all at first glance. Yeah, so what actually, I didn't state the exact statement. So what Gromoll and Ziller proved is, now if you have a cohomogeneity 1 action on a compact manifold, then except for some special cases, usually you have exactly 2 focal sets, two orbits of lower dimension. And if they have codimension 2, they need the special assumption for various reasons that the codimension of both focal sets, of both singular orbits, is 2. And then they can construct an invariant metric with non-negative curvature. I don't think I want to go into it's not very difficult, actually, once you see the condition. And of course, they were assuming for some time this condition just could be dropped, hopefully, and you could get, you could also just assume cohomogeneity 1. Unfortunately, it seems it seems that this is my last remark on this slide, that Wilking and Ziller, and there was somebody else involved. There's no preprint yet, but they're just. I just heard from them that apparently they have a proof that on the Kerber spheres, which also among, they have a large group of isometries if you look at the Brieskorn description, but the focal sets have lower codimage. And apparently they can show there's at least no cohomogeneity 1 metric, metric with a curvature non-negative on the Kerber spheres. Yeah, so this conjecture that maybe the focal set assumption was not necessary seems to not to hold up. Maybe at this meeting in Guayana, they'll all be there. There should be, you will learn more about that, those of you who go there. But in any case, so as it stands, this is the other new, relatively large class of examples of compact spaces of non-negative curvature. Yeah, so let me now just to lead to the metric rigidity problem. Let me discuss the non-compact case. There is the by now well-known Solve theorem, which says that if you have a non-compact manifold, it's already immediately rigid when you look at it. The compact spaces are usually, you don't see any metric rigidity right away, except when the fundamental group is involved in some sense. In any case, so a non-compact manifold always has a compact solve, so a totally geodesic compact submanifold, which is then also of non-negative curvature, and the manifold is diffeomorphic to the normal bundle of that. Yeah, so that reduces in some sense, at first glance again, the study of non-compact manifolds to compact manifolds, which again, we know now is not at all so obvious that is how much of a reduction that is. First of all, we don't know all that much about in the compact case. And the second, there's still this question about the normal bundle. Yeah, so if you look at a vector bundle over a non-negatively curved compact manifolds, then which of them would admit a complete manifold of non-negative curvature, so that S becomes the solve. Again, here, well, there's something. If you ask this question, if you asked a long time ago, no, actually the Wolff-Ziller construction shows that now, at least if you look at spheres, that, for example, all vector bundles over spheres, if the base is at most four-dimensional, do admit non-negative curvature. An example we always had in the very beginning was that, for example, the tangent bundle of the sphere, because it's associated to, so you can just write it as a quotient, in the standard way. So that also the tangent bundle then looks sort of asymptotic, yeah, like this picture I showed you. That we knew for a very long time. But now we can look at all vector bundles over spheres, but vector bundles for higher dimensional spherical base already get very difficult. Yes, and that has to do with the homotopy theory of spheres, and some of these vector bundles are very far away from any nice geometric description, so it's very unlikely they would necessarily have non-negative curvature, or could be given it in a simple way. So in fact, there is an example which is not yet all that satisfactory, which was constructed by Walsher, or in fact, Walsher proved that if you take bundles over a flat torus or a flat manifold more generally, then usually they cannot admit non-negative curvature unless they're trivial. Certainly if the base is a torus, otherwise the rational Euler number should vanish. Yeah? So I don't think there's any example known yet for vector bundles, even over spheres, not to mention more complicated manifolds. Yeah, so this is the yeah, so what are the known results then of, at the topological level? And again, I would say the number of examples, even for non-negative curvature, is a strong topological rigidity. The only known result of great generality is Gromoll's finiteness theorems for the Betti numbers, that the total, it doesn't matter if you say compact or not, because compact is always the same homotopy type as non-compact ones, except for the dimension. Yeah? So the Betti numbers in any given dimension are a priori bounded. That bound is still very bad. It was a little bit, Gromoll's original bound was terrible. Arbrecht improved it a little bit, and the conjecture is it should be that of a torus, so it should be 2 to the n. But we are still far away from that. There's no real progress. In any case, this clearly also, I think, this kind of finiteness shows that topology is very much restricted. And then there are some, the only other general result in the compact case, also very old, is the vanishing of the roof genus on Pontiaghi number for spin manifolds. But that's already a theorem for scalar curvature. That's not really a genuine theorem for sectional curvature. Yeah, so that's about all, and that's known in general, but I think it's fair to say that there is there's a lot of rigidity. The currently best conjecture is still the one that Grove and Halperin, actually I forgot to write that down, Grove, Halperin conjectured that the manifold of non-negative curvature, and again it doesn't make any difference compact or not, should be rationally elliptic, which for example mean one way of saying this is that the rational homotopy groups vanish beyond dimension twice the dimension, or the homology of the loop space is finitely generated also. Yeah. That in fact would give, for some non-trivial reason, would actually give that bound 2 to the n. That's why it's so attractive, and everybody has been chasing this conjecture, yeah, somehow to show that something for the loop space, you can, some boundedness, polynomial growth of Betti numbers for the loop space. People have been trying very hard, but nobody has really been able to zero in on a major result in this direction. So now I want to turn to the to metric rigidity. And let me start by what we all learn in elementary school, more or less, that if you, for example, you take a torus, and then by Gauss-Bonnet, if the curvature is greater or equal to 0, it must be 0. Yeah, this kind of thing for non-negative curvature is typical. Yeah, but in higher dimensions, things like that don't work. And for the n torus, it's true as well. If you have a metric of non-negative curvature, it must actually be flat. Now, this is relates to the fundamental group. I mean, it's more a theorem of the fundamental group, which I didn't really want to discuss. But what's behind it is basically a splitting theorem. Yeah, so if you have any manifold of non-negative curvature, that's what Toponogov proved as one of the first applications of his triangle theorem, that if you have a line, so a geodesic which is minimal in all directions, that splits off as a factor. So it goes through the manifold like an iron pipe. And so then you ask, well, if I take S1 cross S1, I might as well take S2 cross S2. And there already we are at the end of our wits, because this is a famous question Heinz Hopf phrased in the 20s, so last century, which has sort of, it's one of the two questions he asked about that stimulated global Riemannian geometry so much. Now this I've always felt, and I still do, this is the much harder question than the question about that led eventually to the sphere theorem. Yeah, so this is still quite mysterious, yeah, what we should expect here, although there is some progress in a slightly in higher dimensions. So question is, so how rigid? So for example, is it possible? Hopf didn't really exactly, actually it's nowhere written, right? And this is all folklore. But it's Hopf did ask the question, everybody believes. So how rigid is it? Is positive curvature possible, or is it possible at least that you can deform the metric, or you can find a metric, so at least at one point, and then in an open set of points, the curvature is strictly positive, or what can happen? So this is the kind of, this remains for some reason, as a good classical problem should, one of the hardest cases. Now, it seems to me, and others, that the emerging measure of rigidity, in some sense, is the existence of Riemannian fibrations. So for example, being a product. But now in the non-compact case, that was an early conjecture when Shiga and I proved the solve theorem. We asked the question right away if maybe there's more than that. And the conjecture was it should be a Riemannian fibration onto the soul. And that was then in 94 proved by an ingenious little paper of Grisha Perlman. And well, he proved basically if you have any distance non-increasing retraction of the manifold onto the soul, then it is a C1 metric vibration. Metric I use always synonymously for Riemannian. Metric meaning the fibers are equidistant. And Sharafutinov already had shown earlier that such a retraction exists, and that was actually could then be improved to C2, which is what one should probably have to do good geometry. That is still the best we can do. And in particular, see this rigidity, the existence of a Riemannian fibration gives a lot of zero curvature. So in fact, if the soul is not a point, in which case, of course, there's no rigidity, you can deform a convex hypersurface, for example. But if the soul is at least a circle or higher, then there are always two-dimensional flats to each point of the manifold. So to each point. So in fact, there can be no point ever where the curvature is strictly positive. So that's a fairly high degree of rigidity. And so so for that reason, many people believed, and still maybe believe now, that Riemannian fibrations for non-negative curvature are quite rigid. And in some sense they are. But if you think of products, of course, you can deform both factors. What you cannot really deform, or it's not so clear how to do that, is something which is not reduces to a deformation of the factors. Now, for fibrations which are more non-trivial, it's not so. It turns out, however, that the Perelman fibrations in the solve theorem, they look very rigid, but maybe they are not always that rigid. So, for example, Walshap had shown that, now there's always a question, what do you mean? I mean, you can either say you keep the metric fixed, that's one aspect, keep the metric fixed and then want to deform, then usually you can't deform very much. The other aspect is you just keep non-negative curvature, but you allow the metric of the total space to change. Yeah, and then there is more flexibility. So, for example, the moduli space of such deformations is at least as big as all the functions on the base. That's what Walshap showed for two-plane bundles. For example, the canonical line bundle over CPN or the tangent bundle over S2. You can deform very surprisingly. We didn't really believe that was possible. Yeah, so it's not finite somehow. Yeah, so Riemannian fibrations for non-negative curvature have a lot of rigidity aspects, but are not really as rigid as one might think at first glance. So let me mention a few very recent developments in maybe first in the compact case. The compact case is always harder. The non-compact case has I mean, this vibration having flats everywhere it already shows it's more rigid. The reason for that is basically the existence of a convex function. So the boundary condition at infinity serves as a convex boundary, and that what imposes some more rigidity. In the compact case, we are much. It seems things seem to be much more flexible. So the generalized Hopf questions many people have thought about in the past. For example, take two compact manifolds, each one a positive curvature, then would the product have allow positive curvature? Yes, so of course the product metric does not. Or can you free a point? Yeah, can you at least construct some area where the curvature is strictly positive and otherwise non-negative? Yeah, so these things have always been quite non-tractable until now. And there's a beautiful new theorem. Some of you may have seen it. It just came out. It just came out in the Invenciones recently. In fact, now there have been examples. There have been examples of. Well, I come back to that in a minute. There have been examples where the curvature is non-negative. On an open set, you have positive curvature. But Wilking does something new. So he, first of all, it's a very ingenious construction. He looks at any projective space. Then you look at the corresponding projective tangent space. So for example, if you have a complex projective space, you look at the tangent bundle and you look at all projective lines. Yeah, so that's again a bundle over the base, where the fiber is again CPN minus 1 over CPN. You can do it in the real case and the quaternionic case. And for some reason, these spaces fall sort of in the broader area where the Grove-Ziller ideas work to construct non-negative curvature one way or another. Not exactly, but it was sort of very much inspired by these constructions. In any case, so he succeeds for all those spaces to construct a metric of non-negative curvature. Now, these are compact, which is positive on an open dense subset of points. And in fact, the zero set can be quite nicely described. It's not that complicated. The dimensions are in the real case 2n minus 1. Here's the complex 4n minus 2. In the quaternionic case 8n minus 4. Yeah, so for example, if you take, in fact, he proves that inductively, because there are lots of symmetries. You can reduce it to the lowest dimension case. So the construction is actually more or less in the case of RP3 or something like that. Yeah, so in that case, of course, S3 has a trivial tangent bundle, so the corresponding RP3 is also trivial. And so that space then is RP3 cross RP2. And on that's very close, right? I mean, if you think a two-fold covering would be S3 cross RP2, another covering would be S3 cross S2, which is almost S2 cross S2, but not quite. Yeah, so, and in that case, so on those spaces, he has metrics with curvature greater or equal 0, which are positive on an open dense subset. Now, that is not, in spirit, not completely new. It's very nice. But what's really exciting about this is that if you look at S3 cross RP2, you can say for sure this zero set which exists, you cannot deform it away, because S3 cross RP2 cannot carry a metric of strictly positive curvature, just by a very classical argument of Sinch, yeah, who showed in odd dimensions the positive curvature is always orientable by one of the first beautiful arguments in global Riemannian geometry. Very, very classical. Yeah, so clearly that thing cannot be, the metric cannot be deformed to something strictly positive. S3 cross S2 we don't know. But nobody had ever succeeded before in constructing such a metric on a product of spheres. Yeah? Whether or not it's easier in higher dimensions or not is not clear. Yeah, so that is I find quite remarkable. And to see, so those, of course, RP3 cross RP2 also not, because, again, that's not orientable. So in some sense, one would think that if you look for rigidity in variance, then actually the question has been around for, in fact, I've asked the question a long, long time ago. If you cannot get positive curvature, what is the obstruction? So maybe if you look for an optimal, if you look for a metric where the set of zeros is smallest, perhaps one can find some kind of a structure. That is still completely unclear. One can find such a minimal, such a metric. But in these examples, the set is very nice and probably cannot be made smaller. Yeah, so earlier examples of where you had positive curvature on an open-dense subset. The Peterson and Willem could do it on the unit sphere bundle of S4, which is not trivial. Yeah, so that's we had an old example in the 70s where the first example of this type was the Milnor sphere, which is a biquotient of sp2 and an action of sp1, which also had that property. It definitely had positive curvature on an open set. We still don't know if it's actually open and dense, although it can be modified. It's still very difficult to compute, in the contrary to the working example where the zero set is beautifully transparent right away. But of course, in those examples, you never knew if you can deform it away or not. Yeah, that was completely unclear. Yeah, so yeah, so let me see that. Yeah, so I forgot to make a comment here on the last remark. So most rigid, perhaps you would say, if there always exists necessarily a Riemannian fibration. Yeah, so if any metric of non-negative curvature, compact or not, has allows a Riemannian fibration, then it is, I would call it the most rigid, because otherwise, as soon as you have an open set where the curvature is positive, you can very happily deform. Yeah, so there's but you cannot immediately deform if you have submergence. So in some sense, that should be perhaps considered to be the most rigid case. Yeah. Then it might seem, again, that these fibrations are, they're certainly simpler metrics than general metrics, and they have beautiful properties, but they're also not so easy to completely understand and classify, even in simple cases. When I have spent a lot of time the last 10 years, I really have been more and more fascinated with Riemannian submersions, in particular in the non-negatively curved case. For negative curvature or general metrics, I mean, they're always overdetermined and rigid, but for non-negative curvature, they seem to have particular rigidity properties, which they do not have for negative curvature. Yeah, so for example, you can, let me not go into that. You can, in hyperbolic space, easily take a global fibrations by lines. Just take a standard killing field, non-zero, and deform it a little bit, and then you still get submersions. So it's very, very non-rigid for negative curvature. So for S2, actually, I mean, we don't know what happens for S2 in the old Hopf problem. For example, I mean, a very bold conjecture would be it always must be a Riemannian fibration. Yeah, but then again, maybe Wilking will come along or somebody else, and will also construct a metric which is almost everywhere positive. But it's also conceivable in low dimensions, because it's conceivable that there's more rigidity in S2 cross S2 for dimension reasons. And but even if you assume you would just want to classify, vibration metrics of non-negative curvature on S2 cross S2 over the sphere. If you start thinking about it, it's quite difficult. It probably can be done, in fact. Somewhat easier is probably the case. It's the non-compact case, and now I want to talk a little bit about joint work with TAP. You could, for example, look at the corresponding case where you have a product of a sphere with Euclidean space. You have a trivial bundle in the solve theorem. If this has non-negative curvature, it has to be of this form. It could be another vector bundle. Yeah, but assume it seems actually if you have a product, if the normal bundle is trivial, the rigidity is highest. Whereas if you have more complicated normal bundles, it can be deformed more. For example, the unit sphere bundles, like for the canonical line bundles, are spheres, so they have positive curvature, they can be deformed. Yeah? Whereas for products, you have the, well, like S2 cross S2. Yeah? So that was a very good choice of question Hopf made at the time. Yeah, so the question is, if you have, for example, Sn cross Rk, what can you say about the corresponding Riemannian, the corresponding solve theorem there? Or we actually pose the Wyckoff problem, which sounds, more doable. In a moment, I will show you why this general question, although it seems one should be able to do it, it's still very, very hard. And the Wyckoff problem would be this. So we take Sn cross Rk, and then we hope the solve is Sn, which it actually isn't always. It has to have the homotopy type of Sn, but it could be something else. And then you take a tube around the solve. So which would basically then be Sn cross Sk minus 1. So that's a special sort of Hopf situation. And then you ask, can that have strictly positive curvature in the induced metric? Yeah, so that would be a more special. If you think about it for a while, then this should be much more easily tractable because you have, in addition, the structure of this non-compact manifold. So this is a question we asked and called it weak Hopf conjecture. Yeah, so but I should issue the following warnings. There are beautiful results by Igor Veligradek from last year. So for example, if you take S7 cross R5, you can find metrics on that space where the solve is any of the exotic Milnor spheres. Well, I wrote them down actually, right? The ones that are fibered, that came up as S3 bundles over S4. And any of them can be obtained as the solve by some suitably chosen metric of non-negative curvature on the same underlying space. This is this problem that tangential homotopy equivalences, if you multiply with a large Rk, topologically are diffeomorphic. But of course, metrically, it's a different story. Metrically, these things are dealt with, again, with the Grove-Ziller technology. But topologically, this is nothing new. But metrically, it is. So, and he also, Veligradek also proved something even more troublesome. If you take S4 cross S3 cross R5. So for example, you want to prove the same theorem for M cross Rk, Mn cross Rk. You want to understand the rigidity and prove something. Then in this case, you can find actually on the same space, so if you think of S4 cross S3 as M, you can find infinitely many, of the same space, metrics, infinitely many metrics of non-negative curvature complete, so that the solves are all pairwise, non-homeomorphic. Of course, there must be homotopy equivalent, yeah, but they are non-homeomorphic. Yeah, so that's, if you sort of, in general, want to understand Mn cross Rk metrically, which at first glance seems like a relatively doable problem, then maybe this will raise some caution. Yeah, so let me, so however, what Tapp and I were able to do is we looked at the, more or less the Hopf case. Yeah? We looked at the much weaker and easier Hopf case where M2 is any compact two manifolds and 2 manifold, and R2 is, so we look at M2 cross R2 instead of S2 cross S2. But this is non-compact, so M2 can be compact. And we want to classify all metrics of non-negative curvature. And this, in fact, can be done in this case. But it's, again, something at first glance it looks like you should just be able to write it down. When you start thinking about it, it is relatively complex. Yeah, so what turns out to be the case is such a metric will be of the following form. You take a you can find a metric G0 of non-negative, well, actually, no. You take a metric of on M2, and you take a metric of evolution, yeah, with symmetry on R2. In fact, M2 should also have one, although if it doesn't, then it would just act on the last 2 factors. And you multiply by R, where R acts by some translation. So you twist the metric this way, and then any metric of this form is a quotient by an R action, which acts diagonally on all 3 factors simultaneously. The amusing thing is that actually M2 could have slightly negative curvature, and the quotient could still be non-negative. And it's very difficult to precisely say when that is the case. That's maybe also not so important. The important thing is that any such metric has a very precise, explicit description. So usually you have some symmetry on M2, you have a symmetry on R2, and, well, R, they have just a translation. And any metric comes out by this, construction. Yeah, so maybe I can just sort of the way roughly this comes out is you look at the tubes around the sole, and now you're lucky because this is of the type S2 cross S1, so you can intrinsically, and by the general structure theory of a non-negative curvature, they must be non-negatively curved, so you can apply Tabanov splitting theorem intrinsically. But then you have to worry about how this sort of moves up. In each of these tubes splits intrinsically, but out of that you have to construct a global structure. Yeah, and then what you use is the fact that if you have any metric on S2 of non-negative curvature, and you take the product metric with R, that any one-dimensional metric vibration, which is sort of diagonal there, is actually homogeneous. Things like that we did, Gromoll and I did for constant curvature some time ago. In fact, there's these kind of agility theorems if you have constant curvature and you want to understand metric vibration of a given constant curvature metric. For example, on spheres, for example, on flat Euclidean space. Yeah, so that's also turned out to be quite tedious somehow. But this is sort of a generalization. S2 just is any convex surface. And then you take a product and you have some kind of one-dimensional vibration, and you want to show this comes from a Killing field. It's a global argument, and it's for the standard S2. But in general, for any metric, if we had this actually for any compact manifold Mn, then you could generalize this theorem for any Mn cross R2. And the same result would hold for a compact N manifold and the trivial plane bundle over it. Get the same structure for metrics of non-negative curvature. Yeah, that's about, maybe I have these remarks I made about, maybe I should, yeah, this is, because this is older except for Wilking's contribution. So the understanding Riemannian vibration, and as I try to advertise, is really beautiful and interesting and difficult. Yeah, so the simplest case for constant curvature spaces, I think I may have talked about this at some stage last time I was here. Yeah, this came out a long time ago. Yeah, so for spheres, the only vibrations are the Hopf vibrations, rigidly, up to isometry. Yeah? And then the only open case then was S15 over M8, and that in 2 years ago was solved by Wilking, by a beautiful, ingenious argument. There's a problem with all these things. Many of these problems, after thinking about it for a very long time, you find ingenious arguments which are global, and you always think, oh, that's beautiful. Global arguments are always exciting. But it seems to me what we really do not understand is the local structure of submersions, even for 4 dimensions, like by surfaces, even in Euclidean space. Yeah, so it's, if you have any surface in R4 which with flat normal bundle, then the parallel ones give you a flat vibration. But in general, to fully characterize local structure, in fact, I must have mentioned this 3 years ago here as a homework problem, and it's much more than that. Yeah, but the problem with many of these things is that we don't have the local understanding, but we have the global understanding. And the last one that only came out just, which we also worked on for a long time, is actually Euclidean space with Walshap. Came out this year. I think last time I was here, we had it in low dimensions. Now it's just, you also have any metric vibration of flat Euclidean space basically comes from glide rotations, generalized to glide rotations, the way I showed you in the early slide. Yeah, so they can be, yeah, so they're homogeneous. It's not at all clear, like if you think of isoperimetric hypersurfaces, we know they're very complicated. We also know they're just equidistant hypersurfaces. They're just Riemannian vibrations with focal sets over an interval. And we know how complicated that already is. And we also know they are not always homogeneous. Some are homogeneous, and some of the intriguing ones are non-homogeneous. Yeah, so to show that things are homogeneous is always hard, because you have to construct a group. Yeah, so this is yeah, maybe I should stop here.